So, the third lecture of software maintenance. So, this course here. Thank you all for coming this morning. The weather was kind of awful. I noticed that it dips below 22 Celsius. Of course, I drove here from Kotka, so it's a bit there. Longer distance, hopefully, than most of you. But anyway, thank you for joining us today. Today's topic is more or less about the metrics or measurements. What things can we collect? What sort of things can we observe to identify the problematic areas, the broken components, or what sort of metrics can we use to assess what components are too complex, prone to errors, problematic in a sense that they might actually be the cause of all the troubles in the future. So basically last week we talked about quality and how can we understand what we want. This week we'll go through the things that what we can actually see from the existing code base, source code, error logs, these sort of things. What types of ideas can we have there? So basically, last week we talked about quality, like mentioned. The idea on last week's talk was that in all projects, regardless of what type of projects we are doing, whether it's a mobile app or large enterprise software or satellite, for that matter, there's always a couple of breakpoints in the quality. We need to have useful software. That's the minimum requirement for anything, whether it's open source or commercial product. But if we are doing a commercial product or something that's competitive, in a sense that it's not mandated by some requirement that we have to use this product, we have to at least achieve something between the differentiation and saturation points. This means that our product has features which others don't have, has usability aspects which others don't have, or price which others don't have. Like I mentioned last week, even the poor quality can actually become sort of high quality if we consider into the cost effectiveness ratio into this aspect. The example was that god-awful machine gun which won the First World War for the French and the outer allies, well, not the Axis but the other one, which more or less was complete failure of mechanical engineering, but still it increased the firepower enough to warrant it being actually effective weapon or effective solution to that problem, even though the product was of low quality. Similarly, after the saturation point here, we are going towards excessive, which in most cases is no longer actually sensible. Of course, on some things like ultra high-end products, things that the billionaires, multi-millionaires buy or queue for, we might actually consider excessive quality, but these of course are things which most of us probably won't own anyway, or at least most of us won't be doing anything for them. But in any case, these types of quality or levels of quality we have to achieve, and there were a couple of things related to that. First of all, the problem with quality was that even if we sort of kind of understand what we want, we really don't have one definition of good quality in any product ever devised. If we define, if we create a product or service or whatever, we need to define what's the quality we want if we want to go towards some area. This of course meaning that we have to set objectives or requirements or rules or whatever you want to call them for the software maintenance work to see what's worthwhile to fix, what's the cost level, what's the return of investment when we are actually doing something. Or other way around, what do we want to measure so that we maintain the high quality? Or what sort of metrics do we keep getting from our product or observe, or what sort of trends do we want to keep watching so that we understand if our product is going towards better or worse outcome. Because the software bloat, bad compatibility with the existing platform software, failures, unfulfilled requirements, these sort of things are maintenance issues which happen to everything at some point. So what are the things we want to observe on this product so that we at least get on heads up when we find out that there's going to be a problem. Anyway, finally, there was also some best practices, for example, for agile developers. These are more or less related to things like not introducing new bugs into system, not releasing faulty fix, these sort of things, which are more or less common sense. But anyway, these sort of things, these best practices also for the version control and other things introduced on the last lecture, meant that the maintenance or maintainability should be something that's hopefully not that much of an issue. On the following weeks, of course, we are going to talk about the mechanical aspects and re-engineering and revising source code and these sort of things, which are more or less things we have to do when these best practices fail. But if we try to do at least most of these things, we probably are capable of doing some sort of good or acceptable quality maintenance work. For example, the keep it simple is something that's directly actually involved in one of the things introduced today. So, in short, that was about quality. This lecture by itself isn't that much more interesting, I'm sorry about that, but we have to start from somewhere. We have to understand what are these maintenance or maintainability measurements, or what sort of things can we use to observe how to maintain the software before we can actually start doing things we consider important. So, what is measurement? Sorry about that. There's some scripting things I didn't expect, but well, let's get them here. So the uses of measurements are that the measurement is something that's defined and it produces a result which creates trend, and it's comparable to previous measurements. It's comparable to previous results, and we can understand what happened and why things happened when we measured the thing twice and something happened in between these things. So it's more or less a thing to understand what sort of changes are happening. It means that we can understand what the current state of the system is, or how well our last fix, for example, worked. If we wanted to make the user interface more fluent or fix stability issues with the mobile version of our application, we might want to measure something like mean time between crashes or mean time between errors, or something to that degree to see if we actually get the thing we wanted. Also, if we measure things, we can get control of the software. We have the ability to predict things. We have the ability to measure, for example, something simple like, do we have enough content for our players to use in our game? Do we have to add more content this week, next week, at all? Is this actually even profitable product? to be not to consider some engineering aspects, like are the players, for example, using one strategy or one component or one unit or one nation, for example, on the 080 example, at all. And if we can measure this and we see that they aren't, or that there's something that we didn't completely predict, we also have to find out why these things are happening. Why aren't the players doing what we expected them to do? What are they doing, and why is this happening? For example, is our game design broken? Do we have mechanical problems there? Is some usability aspect problematic? For example, too many clicks or too many actions which require unnecessary amount of finesse to complete, to keep so that the users don't want to use, for example, characters which require micromanagement, because in our game the micromanagement isn't possible. These sort of aspects. On the more formal or serious side, for example, do our customers understand all the points in the forms? For example, I have been trying to do a customs declaration with the system for the Finnish border control, and it's complete freaking nightmare. It keeps asking me for things which I have absolutely no idea what they are. Something like the ID code of the container my package was in when it arrived to Finland. How could I actually even know that? So of course, for consumer product, that's a terrible thing to do. It's completely horrible design. But on the other hand, considering that if it's something that's meant to be used by professionals in the logistics hangar or somewhere else, it more or less might be required information. But on this aspect, you should measure, for example, how many people actually outside the building or establishment actually are capable of using that product. So even usability is something that can be measured, and there's ways to do that. Finally, of course, we want to improve things. So if our aim is to improve or encourage people to do the work required, usually done by some bureaucrat, for example, like with the customs declaration things for package arriving from overseas, then we might want to measure how successful people are usually doing that. Because I could, for example, argue that I'm probably not a complete idiot. I might be still, but usually I should be able to do that on the on the online service, to fill out the form and get the package on post with the customs bill with it, so that I have to pay this much for the government because I bought a wristwatch from some place which wasn't in the European Union. However, I couldn't do that, so of course the service could be improved. And of course the usability, even though it's one of the things that usually we consider that that's something that needs to be improved, or the added amount of content, also technical aspects like, is this fast enough? Is this responsive enough? Is this effective enough, so to speak? So if we want to, for example, make our online shop better, then we should have some sort of an approach where we get the first search results or hits very fast, and we only research more or ask more for or look for more when the customer isn't satisfied with the first 5 hits or something like that. It's an optimization game, really. Or in other ways, can we cater to enough customers at the same time, or users at the same time? These sort of things are things that we should measure, and so that we can understand what's going on, and that allows us to improve things. Because of course, this works also the other way around. If we don't measure these things, we can only guess about things. And on the scale of university assignments, it's okay to guess, because who cares, really? If our product or demo or proof of concept isn't good enough, it isn't good enough. But if we are working with something that's actually meaningful in an economic sense, that we are paying people's salaries with that product, we never can actually do the guessing work. We should base at least on some assessment. Even though, for example, in the games development, of course, people say that it's not sexy or it's not the style of the industry, or so to say, that we measure things, we predict things, we use these sort of approaches. But my personal opinion is that that's complete bullshit. I mean, all the products which actually are successful in the games industry are the things where you know exactly what the player was doing, why the player died, why that content didn't work, what the player was doing. Can we show them more ads, and this or this, and so on and so on and so on. So even though this is not sexy aspect of software engineering or software maintenance, it's also still something that you have to do. So there's a couple of things here mentioned which more or less are aspects we sort of kind of know. But on the other hand, we also can't say that it actually works like that. So the first one is the developers who drink coffee in the morning produce better code than those who drink orange juice, or that the more you test the system, the more reliable it will be in the field, or if you add more people to a project, it will be completed faster. So some of these might be true. All of them might actually be true to a certain degree, but they aren't inherently true in a sense that, for example, the second point, the more you test the system, the more reliable it will be in the field, works to a certain degree. But after testing in a laboratory or alpha testing in a small scale, you will run out of things to test. Well, realistically test. Of course, you can spend your time from here to eternity doing some stupid low-scale unit testing, but still you at some point should move to the field, because that's a place where you find complete new set of problems. So you need to measure when you have to move to the field or to large scale or the full environment to actually test things. Also, if you add more people to a project, it will be completed faster. Works for some people, for some projects, or for some time. Unfortunately, it will not always work. There's a rough estimate saying that you can halve the project time by throwing resources at the project, but you can't complete it any faster than the half of the time, which is the sort of a sensible estimate. Meaning that if you have a 3-month project for one person, you can't throw 100 people into the project and expect it to be done tomorrow. No, of course it doesn't work that way. But if you throw something like 10 people to that project, you might have something sensible in about a month or 6 weeks. Because you still run into the same problems, you still have to rewrite the source code and so on and so on. So of course you have to measure things. You have to see if everyone has something to do, or if we actually are getting new bugs, or what type of bugs do we get, or how do we get them, when do we get them, and why do we still keep getting them. Finally, of course, the developers who drink coffee in the morning produce better code than those who drink orange juice is something that requires setting to measure. So who drinks coffee, who drinks orange juice, and at some point you might also want to consider that those who tend to drink coffee are put to drink orange juice, because usually the code is, the quality of code is usually kind of related to the experience and capabilities of that person. Some people are born naturals in programming work, some people just don't get the idea of programming, but everyone can learn up to some degree, and then the rest of it is talent or capability. Same really with basically everything. You can become sort of a semi-professional or even professional by training and learning, but it doesn't hurt to have some natural talent involved. So these all things require that we actually measure things or create metrics to understand how they function. And same with everything else. So last week I showed you this slide. What the quality standard actually measures. So there's a wealth of things we can actually measure. This is the main idea of this slide. We can measure the actual data, or we can measure the quality in use, or we can measure different aspects of the product quality. So we can measure several things, but for example, we still lack some aspects, even with that quality model. For example, the different stakeholders might have other things they want to consider with the product quality, or the computer hardware, or the non-target software related. So how easily manipulated is that product, for one example. But still, these sort of things we can measure from the software. The problem, of course, with the software is that it doesn't have size, it doesn't have shape, it doesn't have standardization in a sense that even if you are doing something with Lego blocks, you still have the certain types of Lego blocks, and if you are doing building construction, building architecture, you have some idea on what will work and what won't work. For example, the building will collapse if it's made entirely out of glass or something like that. But unfortunately, on software engineering, we don't have those sort of things. Still, even with this restriction, we also have the problem that we also have people involved, and money involved, and management involved, and all these other things involved. So basically, we can measure these three things: the product, the process, or the people. And unfortunately, I know that it might sound a bit weird or a bit stupid in a sense that this is a software maintenance course. Why do we measure people or processes? But all these things actually affect the software quality or the maintenance work, or how much money, for example, do we need to develop something, or how much time, or what eats our money and time, in a sense that it's not just something that we need beforehand, but if we want to make something lean or more easier or react faster to the market situation, we have to know what's eating our resources, because everyone has a finite amount of those. So the product, of course, is the product itself. The documentation, deliverables, source code, service system, the cloud network, or the server cluster, whatever we use to run the software. So we can examine things, functionalities, size, how much money have we already used, all these quality attributes mentioned by the ISO IEC 25010. So there's not really that much new into this problem. If we want to understand how much money we would have to use to make or create, for example, one new attribute or ability for our software, we more or less have to decide or calculate how many changes do we need to make, how much complexity that would add to our product, and then based on that use a cost estimate on how much working hours or time it will take to design, develop, and do the quality assurance work before putting that attribute out. So if we measure the process itself, it of course means that we are measuring all the other things revolving around the work. So it more or less means that we are measuring the organization or the ways we are doing things. These can actually have some very interesting results. For example, on one occasion we were doing a sort of a interview or analysis on one company which was developing mobile phone operating systems at the time. And it wasn't Nokia, I can tell you that much, but I can't say the name of the company we were working with. But they had a really simple problem. They were doing testing work on the support applications of the operating system. So seeing that everything works, that the control panels and these sort of things work like they are meant to. But they had a really stupid problem in their process. They didn't have as many test system licenses as they had developers doing testing work. So even large international company ran into a problem where 20% of the workforce was simply just waiting that they can get access to their software, because the system was locking out people when there were too many people at the same time there. So of course, that's one thing that causes problem with the process. Of course, on software lifecycle or process lifecycle, this could also mean some simple things like that we don't have enough developers, we don't have enough test users, we don't have ability to make decisions, for example, on how some aspects should be tested, or if something is good enough, or that the test automation needs upgrades. We have to maintain our existing test cases for the entire iteration because our system is already failing. We need to upgrade this, we need to upgrade that, because these are all process problems. The infrastructure ensuring that we can do development work is crumbling. And because we are talking about large amounts of money here. For example, I know that on one mobile application company, they were doing migration work or upgrades to their existing code base and their development tools. It meant that the developers were actually doing nothing else than this support work for 3-4 days to upgrade everything and check that everything still works. You might consider that that's trivial amount of work, or that it's a trivial cost for actually running things, because that's something that you have to do. But take into account that actually having 5 programmers, software developers, working for 4 days is hideously expensive thing for a small mobile application developer. So do you want to spend money on that, or on developing and testing your new version of your application, or trying to fix existing problems so that your customers actually see that you are doing something? Because it costs thousands of euros. And of course there's also the problem that what happens if the upgrade fails? You have to go back to the old system, which takes yet another couple of days, and you end up spending 10,000 euros of money finding out that we can't upgrade to the newer version of Java or Android Studio or something like that, because then our build won't work. That's a huge bill for something that also interrupts your development work for an entire week. So of course you don't do that unless you really have to. The tools or the libraries or the auxiliary systems you are relying on no longer support your development environment. Then you have to upgrade. But this is also something that you have to measure, because that's part of the process. Finally, there's measuring the people. Well, of course, there's a couple of things that you can measure. So, how fast do they work? How many tickets do they complete? How many problems have they introduced? These sort of things. But of course, these are really unethical things to do. I'm not saying that it's completely wrong to see that your people are actually doing something, but still, surprisingly, people don't like being turned into numbers. So if you are making decisions purely based on the thing that, okay, we have been observing your work and you are not good enough, goodbye, you're fired, you will not win any prizes really. But still, you have to, of course, you can also use this other way around. If we have people who are really talented, we of course have to use those people. But on the other hand, if we are just giving them to everything to do, and the other people just wait around for the talented people to complete everything their team was tasked to do, we will end up with the two things. First of all, the people who are less talented, they are just wasting money. They have nothing to do, so give them something to do, and you will lose the talent because it seems quickly that you are just abusing him or her to get everything done by them, and other people are just looking from behind, cheering as they do the work, or they have to carry all the responsibility while the less capable people are not required to do something and they still get paid like the talent. So that's of course a problem. But that's also a thing that you only can know if you measure things or see. Who commits things, who completes tickets, who closes bugs, these sort of things. So it's a really simple aspects of maintaining your workforce, running your project or running your team. See that everyone has something to do and everyone is doing something. So, the problem, of course, is that everything you collect has to provide useful information. It has to provide useful information, and it cannot be a problematic or being a burden to collect. Of course, you can collect whatever information you want to have, but it always should be something that provides more value than it costs. Of course, it shouldn't be a huge burden to the development team because it's always time out from them doing the actual development work. Also, this of course means that you should try to use automatic tools, and that can be expensive, and that's of course the problematic thing, the expensive here being the operative word, which means that you will probably not get money to do everything you want to do. So you can't always rely on the fact that there's a tool that will gather you this piece of information, because not everyone is willing to pay that money. If you have been doing the project work on this course already, you will observe that it's actually really laborious and also really hard to do some advanced features of some software things. For example, I know personally that Intel has a system where they just put the artificial intelligence and neural network to test out everything in their software. The neural network plays sort of a user who has a faint idea on how the software is used, and then it just keeps doing this monkey test automation, pushing different buttons, seeing that all the branches and all the different ways to completing things actually work. Of course, it's nice to have that, but at the same time, you have to have the Intel money to do something like that. Or you have to buy the license and design your software so that it actually uses the framework. And that isn't that cheap. There's also an open source version of it, or open project sort of version of it. But then it comes with the problem that there's absolutely no support or warranty for it. If it breaks your entire product, then, well, it breaks your entire product. And these sort of problems. But anyway, these are more about the collection of the data. So, there's a couple of things here. These aren't really rocket science, and these are also something that's covered on the software engineering methods and models course. Hopefully were covered. So we're not going to go too much into these aspects, but anyway, the big idea here is that you should actually do things by designing what's relevant information for you, and then systematically collecting it, and then systematically analyzing it. It's not that big of a deal, really. So there's also a couple of larger companies as an example here. For example, what Motorola, a huge mobile telecom company, did, or what sort of things they do. Well, they use their own metrics programs for 7 goals. It's nothing really interesting. Improve project planning, decrease defect containment, increase software reliability, decrease defect density, these sort of things. But the important part here is that the Motorola is one of the companies which more or less produces everything which has electronics in it. So they have 7 goals which they try to focus on each of their programs. And of course what they measure are delivered defects, process effectiveness, software reliability, these sort of things, but which really more or less all support all these 7 goals. Similarly, IBM has software measurement program. They are looking into something like customer satisfaction, post-release defect rates, customer problem calls, fixed response time, these sort of things. Surprisingly, Motorola was looking into their software engineering aspects, into their defects, or they're focusing on their bugs, what are the known problems of their products. IBM is more or less looking, well, also the same things really, but they are looking into the customer satisfaction. What are the problems that actually matter? Because if you have enough users or if you have enough products, you might also want to consider the fact that your brand is really valuable. So what do the customers think are the most problematic areas? This is also something that Apple used to do really well. They sold overpriced products which were designed to be, completely error-free or problem-free until the warranty was over, and then they died, and then you buy a new one. That was more or less their thing. The laptops are still built like tanks. You can drive a nail to the wall with the Power Mac because it's solid aluminium. So of course, that was something that's about customer satisfaction, and that was the only thing that actually mattered. If the customers don't notice this problem, then it's not a problem. So this is sort of something like the IBM is doing, what the Motorola clearly wasn't. And finally, HP, the Hewlett-Packard, they also ran things like defect metrics. Of course, with the HP, you have to understand that they are still, I guess they still are, in the customer electronics. So they had lines of smartphones, video cameras, PC computers, at least desktop monitors. I think they were trying to do television sets or TV sets or something like at one point, and also printers and stuff like that. So of course, they provide things for office. If you go to, even this one here, this is an HP laptop. Our university uses HP laptops now. So, of course, what it means is that our university here, small regional university in Finland, we are not a meaningful partner to HP. They really probably don't give care about what we are doing here. But still, on their products, they are testing like average reported defects per working day. Because universities like LUT, there's hundreds of them. Industrial complexes, office buildings, all these other places which use HP products. Of course, this is an important thing for them because they know that they don't really have to care about one customer. For example, I'm a professor here, but I couldn't affect the decision to get the HP laptops. It was made by the board of directors or someone from the upper management. So of course they don't have to give a damn about the customer, but they still have to care about the average reported defects. Because if they release a product which fails once per week and deliver that to all the 500 million people there serving for the work laptops. It would be a complete freaking nightmare. Nothing would work and the company would tank instantaneously. So that's why this is the metric they are interested in. Apple perhaps not that much. IBM gave away their laptop game, and also Motorola is doing something different. But anyway, this also means that these three companies, also the Apple, fourth I mentioned, are sort of similar companies by the first idea. So you'd expect that if you go to their development project, making a product, service, or tool or application or whatever, you'd run up against similar metrics, similar things to measure, similar things to observe, but surprisingly, that's not the case here. They focus on completely different things because those are the things that are actually important to them. So, going further into the actual measurement work. So, this set is more or less about what sort of things we could use to understand or identify the problematic modules or things, or see how well our system is doing. Of course, there's a couple of things like what's a measurement, what's a metric, what's an indicator, and these sort of things. Of course, I'm not going to read these for you because I am fairly certain that each one of you can actually read, and these are more or less basic English things. So let's not get tangled on that. But anyway, there's a couple of things that you'd have to understand in all the measurements we are talking about. These are also important things for the project work itself. So we have to have measurements which are reliable and valid. Means that the reliable has to have consistency every time we use the measurement. Similarly as validity means that it has to really measure the thing that we want to measure. Of course, these both have some problems if we don't understand what we are actually looking for. These, for example, here are the representations of different types of problems. So this one is reliable but not valid. It gives accurate results. Unfortunately, they are all off. This is valid but not reliable. It's centered around the correct place, but it's still too inaccurate to give you real good result. And finally, this one is reliable and valid, and it would actually give you 1 day of leave of absence from the Finnish Defense Forces if you manage to do that with the assault rifle shooting competition. Anyway, but we want to have this because, of course, it's the best situation. But you have to keep in mind that there are measurements which are reliable but not valid, or valid but not reliable. One very simple example is the source code, amount of source code. I'll be measuring the amounts of commands or the amounts of lines of code. Because the amounts of commands and the amounts of lines of code is completely different things. The other one includes the commentation of the code. And also, why should we care about the comments? On the other hand, we know that we have to comment our code. We have to have the conventions so that the maintainability stays up. So if we are trying to look for something like maintainability, we also have to include the comments to the code. But on the other hand, the comments themselves don't do anything, so they are not adding up to the technical complexity. So if we are trying to identify things like overly complicated modules just by checking how large module source code files we have, or how huge our class definitions are, of course that's not something that's clearly immediately obvious, because there's a real problem that we measure a wrong thing. We want to know the real thing, but we are not getting accurate results. So we get valid but not reliable, or reliable but not valid, considering that we might identify the largest files, or we might identify the files which have huge amounts of comments, but they actually but the module itself isn't that complicated thing. It's just well described what it is doing. So, of course, if we go from small startup company or 5-person game studio or something like that to an actual real organization, huge company, huge project, even open source project, which tend to be actually quite huge in general, we need the measurement plan. So why we measure things, what we measure, who will measure the things, what parts of the system, when, and how the data will be collected and analyzed. Because like I said earlier, if you have a measurement which doesn't produce reliable result or something that's comparable to earlier results, you are just running into a nightmare. So basically, these aspects here, so understandability, ease of use, are all attributes of things that's fairly nice to have. Of course, you can always have that, and you might want, you tend to end up using something that's based on the tools you have or the infrastructure you have. But still, on some occasions, you might actually want to design a feature based around something that you want to measure. For example, this is fairly simple example, but I mentioned earlier that all the game studios which have been successful have been really accurately measuring what the users are doing. And that's actually something that wasn't until recently well measured or well supported by, for example, Unity or Unreal engines. So the company made an addition to their product which more or less sent the end state of the player's character, why it died, where it died, the location on the map, what enemy killed the player, and these sort of things to their server. Of course, if we are talking about mobile game and we are talking about the own server and sending something to server from the application, that's an data privacy nightmare to do. But still, that was something that had to be done, because you need to be able to modify or fine-tune your product, and that's really expensive thing to create, just to have one measurement which tells us what sort of things the users are experiencing, or what sort of problems the users are experiencing when they play with the product. Overall, these are the requirements for any measurement ever. So it has to be objective, it has to be reliable, it has to be economical, and it has to have reusability. If one of these things is missing, then you can scrap that. It's a waste of time. Find something else. Simply because all these things are based on reality. You might have a measurement which is not economical, but you will never use it because it's so expensive. You might have a product which for one time tells you, are we ready or not? But if you run into the problem that it says that we are not ready, then what the hell are we going to do now? Also, if it's not reliable, it's completely unusable. And of course, if it's not objective, well, you might just pull the number out of your ass, because that's really what the objectivity means. You can't rely on something that's based on purely opinion. But on the other hand, a statistically analyzed amount of opinions is completely different thing. For example, with the usability studies, which is something that's really focused here because usability makes or breaks the product economically. Of course, you can't just upload information from the user's brain, knowing that how much did they like this product or what sort of solutions do they prefer in general. But if you have enough opinions, then you have an objective measurement that most of the people in this group seem to like. But anyway, also there's of course the test process standard, which is other thing from the quality standard. Yet again, the amount of different measurements or indicators identified by all these things are so huge that we are not going to go through all these things on the lectures. But on the other hand, it's a good thing that you actually know that they exist, so that you can actually see what sort of stuff there is. So the raw general data measurements are things which are fairly self-explanatory. They are things that measure, for example, how much money have we used and how much time have we used, and are those in any way comparable to each other. How many features have we completed, how many features are still missing, how much content have we created, how much content is still missing, how much money have we used, so on and so on. Simple things really. The work plan based indicators, the project status indicators, they are based on the documentation. For example, are we still on our schedule, or are we, how many tickets are we closing each day, how many bugs are fixed each day, how many critical problems do we still have, these sort of things. Or reliability or testing efficiency. The testing efficiency here means that it's how many problems did we find, how many problems did we fix. If we want to go fancy, we might do something like seeding errors into modules and seeing how many problems our environment finds to get an idea on how thorough the testing environment or the testing tools are, but that's something that's rarely done on real-life software development. Of course, some companies do it, but that's something that's not nearly every organization does. So, the quality measurements, on the other hand, these were mentioned last week. They are on the standardization, which I, by the way, haven't yet uploaded. I will put that file, or the one of the draft versions of the standard online at some point today or at the start of this week. You shouldn't be fooled by the fact that the version you see on the course pages is a draft. It's a draft for comments, but it's the final draft, so it will be the same thing as the real standard will be or is. But it's just that because we are doing research and teaching related to these standards, we are not allowed to distribute the actual final version of the file, but we can distribute the final draft version because that's how the licensing works. Of course, the basic measurements in this scenario and all the others mean that they are simple enough to count from any type of system or project. Remaining budget, lines of code per feature, lines of code against commented code, amount of modules without commentation, and these sort of things. So basically really simple things, usually something that should be supported by any infrastructure you are using to maintain your software or develop your software to that degree. So these are also more or less the things that we are expecting you to be able to come up with on the course project assignments. Of course, they have their own list, but these things are something that if you can't observe or calculate or see these, if you don't have access to the information which allows you to see all these things, and you are called a project manager, then you are more or less played for a fool or a scapegoat for the project when it fails, because all these things are really basic stuff. Of course, there's some things that actually also help in addition of these measurements of understanding how probable it is that something fails, or how much it will cost to develop something, or how laborious it is to create something. For example, on the first lecture, it was mentioned that there's usually the 80-20 rule for all software development. That 20% of the components include 80% of the problems. So it would be wise to identify these things before we actually start development, because then we know what are the things that we need to focus on. If we start with some new software, or you are assigned to maintain or further develop a existing product, it might be good information to understand what are the actually complex parts. And there's a couple of measurements which you might find useful in that aspect. Of course, they are very detailedly explained on these slides, so we will go through them fairly quick. Also to keep this lecture in 1 hour and 30 minutes or something like that, because we have already been talking about these things an hour. All your faces are so excited to be here that I think that we might want to skip towards the end, and you can read about these things afterwards. So the first one actually is the function point. So why do we measure size? It's easy to measure size. But how about the functionality offered by the system? So it's really simple calculation. What happens when we use this thing? The function points are inputs, outputs, abilities to do something, the amounts of files we are using, the amounts of files we are creating. It's fairly simplified complexity calculation. So the function point, if you have high function points for one module, it means that this function or this activity is complicated, or it does complex things. So the major components, including external inputs, external outputs, internal files, internal files, and external inquiries, for example, calling online, seeing something from online library. How many of these things happen, and how many times do they happen when we are using this product? So, something like this. It's a fairly simple way of understanding how complicated this function is. For example, on the next example, if we consider these sort of aspects or specs, we will see that it's actually fairly simple to list what needs to be done, what we need as an information, what needs to be done, when does it has to happen, how many files which outputs is it creating, inquiries from external system. So these sort of things which need to happen. So for that functionality or the module or the things that do that activity, we end up with a function point complexity of 28. Of course, by itself, it doesn't mean that much. In general, however, it means that if we are trying to add more complicated things, it of course costs more money. Also, it probably introduces more problems, it introduces more bugs, it requires more people who are more capable of doing things. So fairly simple way of accounting for functionalities. Of course, there's also a problem with that. There's always a problem in software engineering with everything. That's really annoying thing about this area. But on the function points, of course, it used to be used, or it was created in IBM in '79, so it's not exactly something that was developed with the smartphones in mind. So the problem was that it actually tends to correlate very closely to the lines of code estimates. So how large these modules will be, or looking backwards, the amount of lines of functional codes correlates the function points. So there's extended versions of these. For example, several systems which account for more finer details, like how many views does it need to have, how many unique user interface elements does it need to have, how many buttons, how many views, how many things, how many these sort of things. And I know for a fact that, for example, the scope management at Kokomo is Kokomo 2 actually, is something that's still taught and used in the industry. Not during the development work, but for example, when we are assessing how much something might cost us to develop, so that we can participate on a request for projects or something like that. We know how much it might actually cost, so we have an idea how much money we want from the customers to develop this feature. Other way around, if our customers request a new feature, for example with free-to-play game, we know how much money it might cost us to develop this to our product, and if it ensures that we get more money than that, of course, then why not? Otherwise, we just end up with that bill to pay. So, of course, these extended versions have several more things than inputs and outputs, and that's more or less the idea they have. They all share the same idea. They all follow these sort of things. For example, performance of the system, transaction rate, reusability, installation ease. They are sort of multipliers on how complex or how many functionalities things have. Does it need to call somewhere? Does it have to be able to update itself? Or is it something that's just doing its stuff until the sun explodes or something like that? And finally, applying maths here, value adjustment factors, basically just a symbol of sum of things. We end up with a multiplication, and finally we get a scoring sheet for the different things. So how much these things are required, how many, for example, these things affect the product, and we get the final answer. So this is more or less an extension. It takes into account more things, but it's still the same function point analysis. So this is something that's usable even before you actually develop anything, or if you are trying to find the more complicated things. Of course, on this product, the multiplication actually meant that it's actually not that the score was a bit lower, but that's also something that might happen. So if we make more fine-tuned analysis, we might find out that something isn't as bad as it used to be. On the other hand, if we want to assess complexity, there's a really cool sounding cyclomatic complexity metric assessment by McCabe in '76. This is something that assesses the complexity of one module or one source code or one solution by itself. And it's actually very effective measurement, because it actually predicts quite well the problematic areas, how costly something is to maintain, how badly this product will fail. Of course, this doesn't tell you anything. It's just mathematics. But actually what you have to understand on it is that it's actually a fairly simple thing to use. It's a calculation of how many different paths from start to finish there are in that particular module. It's nothing more complicated than that. So for example, here we have made a activity diagram of one module doing a simple output too big, output too small, guess the number game. So for this, the cyclomatic complexity is 3, because there's 3 unique paths to complete this module. It's not that difficult, really. So why is this important? Because this is a good metric for testability, maintainability, and usability in general. Actually, it also has stupidly easy thing to remember. If your cyclomatic complexity for one module is greater than 10, then you might want to split that up to 2 modules, because it's something that has too many variables, too many variations. Something will screw up there. There will be something that ceases to function correctly, and then you have a problem. And this is actually fairly well accepted in the industry. Keep the code simple. One of the first best practices of agile developer. And last with everything, it's not rocket science really. But still, the cyclomatic complexity is a fairly good way or measurement to assess or predict what modules will fail and what need revision and re-engineering in the future. But that's a thing that we will talk about more in later lectures. So there's also a couple of other ways to measure or assess software complexity or costs or problems. For example, Halstead's software measurements. These were also done during the late 70s to assess how large some program is, or how expensive it is to develop, or how difficult it will be to develop. The premise here is that any programming task is just arranging a finite number of program tokens, meaning that you have to add finite number of commands, logical gates, variables, different things together to make something happen. And based on that, you actually have some numbers or primitives which say, for example, tell how large the program will be, how large it is already. And these primitives can be defined into a series of equations. Like something like that. So how difficult the change will be to do, how many faults it will have, how much effort, working hours it will have, how large the changes will be, how many problems there will be in that software. There's actually also another number here. The professional developer makes an error once every 3,000 decisions. So that means that if you have more than 3,000 moving parts, it will have at least one problem in it. But these sort of things are assessment models. You have to understand that these are sort of rough estimates which give you an idea of how much work needs to be done, or how many errors there probably are, or what are the areas you should focus, for example, your test automation on. Some things which are simple and just do one thing when they are asked to do so probably aren't going to fail because of quantum fluctuation. But if you have complex modules doing several things, sometimes even at the same time, if you also have parallel modules or parallel computations going on, these are the places where you will find the problems, and these are the ways to identify and assess which are the ones that require most of your attention. So there's also some other things which can be used to assess the problematic areas or problems in general. For example, the defect arrival pattern. We will always have problems. We always have people reporting things, and we always have problems found. But on the other hand, it's not always trivial when and how they are found. For example, the arrival patterns can look like this. There's a quite relatively the same amount of errors in all of these. But for example, we can see from these that do we actually have something that works or not. For example, here we probably have managed to fix most of our problems because the amount of new defects is decreasing. Of course, with the same amount of problems, why is this rising constantly? Why is the trend upwards here? Or here it's plateauing, so we probably have found most of the serious problems. Here we are experiencing catastrophic situation. So what can we expect in the future? On this work here and this work here, we probably can start to ease off a bit about the maintenance work and focus on adding new content or making new changes or additions or new features or such sort of things. Whereas on this side, the system is still not working correctly. There might be a faulty fix here, broken fix here, or simply something isn't working correctly. We have to revise what was done and then see that what we changed and why are we seeing increasing amount of problems. Even with the same amount of errors, when we found out them this way, we can sort of see that, okay, this fix or this maintenance cycle was success, this maintenance cycle was, well, something else. Also, well, you can try to predict these things, try to use these to predict several different things, but the important, of course, is to keep backlog, because you can see that what was done, we can, for example, take back or cancel the previous patch, fix things that happened earlier. This is also about the best practices of using version control, because if we do patches one feature or fix at a time, okay, the last one didn't work, let's take that out or fix it again. Finally, something like phase-based defect removal pattern. This sounds really fancy, but on the other hand, this is more or less about the process. Is it working or not? So, when most problems are found, this is about development work, also about maintenance work. If we find or found most problems during the design or code inspection or during the actual testing work, or somewhere else, which meant that actually when we went to technical testing, doing the actual quality assurance work, we found only a couple of problems. Means that our design planning work, this project works or this process works because it's capable of weeding out most of the problems. Here, if we find most of the problems in system testing or unit testing, it means that we perhaps aren't doing as good job as we should be. For example, on planning on what to do this time, or what sort of changes to do, or what sort of additions to do. Or, for example, we are too ambitious here. If this is an iterative agile development work, this means that we are probably adding too many things at the same time. We design the changes and then try to cram them together, and the system fails because it's technically more difficult to do huge steps over the number of small steps. Okay, so other things, fix quality, how many broken patches there are, fix response time, how much time does it take to fix a problem, and fix quality, for example, was something that IBM was looking for. So these sort of things also tell you that if you are doing maintenance work, how many patches worked, how many fixes worked. So you might be doing something right if you aren't constantly battling with the fixes that break more things than actually fix. Well, on the peoples, on the other hand, the cost per function point, mean time required to develop a function points, defects per hour, these sort of things. Also something that you might want to measure, but like I said earlier, people don't like being measured or negatively competed against each other. There was actually a fairly funny story about the gamification of work in one Disney resort, where there was a simple competition between the hotel maid service units about doing the laundry or units of laundry and setting the rooms. So the team that made most rooms during their shift during the week won something trivial like a chocolate bar every Friday or jug cake or something like that. So of course what this meant that the team started to sabotage each other, adding concrete mix to the washing machine or gluing the locks on the maintenance cabinets closed so that they couldn't do their work. Because it was a competition and some decided to cheat. Simple as that. So gamification failed, and also because it gave the people wrong idea, wrong impression, and measured people against each other, me saying that some people don't get something because they aren't good enough. That's not really a good way to approach this thing. So, what to remember from this lecture? Okay, first of all, the definition of software metrics and measurements, and of course why we want to measure these things. Also the different types of measurements, and especially the function point analysis and the cyclomatic complexity and these latter part things, because they are something that's really software maintenance centric. They were developed in the late 70s, which means that they are older than each and every one of here in the room at this point, but still they are relevant ways of assessing if something is overly complicated and if something needs to be revised or if something needs to be re-engineered, or if we want to export our product or software to another platform or architecture. What are the first modules that need, or the most probably problematic modules that we need to take into account? Because if those work, then the most complex and problematic areas are already there. Rest is easier. And it's always a fairly good idea to start with the most difficult one, because if that is successfully updated or migrated, then everything else will follow. So finally, there's now 4 or 5 groups, I don't remember which, but still there's plenty of you here who don't have a project group and don't have an open source project. So get both of them. And remember, only one team per one open source project. So if you are fast or one of the first ones, you can pretty much select whatever fancies you. Otherwise, you get what's left. So that's that. Next week, I actually have absolutely no idea what the next week's lecture was, but it's on the Moodle. The exercise assignments are already also in the Moodle, and we will be giving the next lecture next Monday, like today here. So go check that place, start doing the maintenance project on 0AD, start doing the project assignment. And I will inform you about the person speaking on the the visitor from industry lecture as soon as I have that person booked. I have a couple of ideas. Let's see which one we get. Okay, good. Thank you.